A low G value can compromise daylight access, and it's challenging to balance both. There are so many glazings on the market. I came to meet with Fabio Favorino, an expert on advanced glazings at Politecnico di Torino, so that he can support me in the selection of glazings. Let's say I want to design and pick up the right glazing technology for my facade, and I want to make sure there is a good performance in terms of daylight and visual comfort, and then of course lighting energy, but also thermal comfort and thermal energy, heating and cooling.
Okay, so there are many technologies out there, and I think the two main parameters that we are looking at, like besides the U value, are visible transmission and G value. Okay?
Right.
So if I may, we can basically describe
Even better. Thanks.
all the technologies in one graph, where we can put visible transmission on this axis, so between 0 and 1, so maximum is 1, and G value in that axis, and the axis, x-axis, maximum is 1. So all the technologies can be classified in this space apart from one part, which is, we have a physical limit here, which is basically about 2.4 and something, which is given by the ratio between the total solar energy transmitted in the visible spectrum and the one transmitted over the whole spectrum outside the glazing. So just the solar radiation. In the visible spectrum, you transport more or less 42%, 43%, and that gives this physical limit, basically.
If I understood correctly, to describe a glazing in terms of how good they are in terms of TVs, therefore the light transmittance and total solar energy transmittance, is very nice and very important to see the relationship between these two parameters. That's why we're using this graph. But effectively, a glazing would be a point in this graph,
Exactly.
which is described by a specific TVs and a specific G value. But what you're saying with this physical limit is that we cannot be in this area. There are no glazing technologies that can be here.
So a normal glass, like float clear glass, would be with a TAUVIS in the order of more than 0.9, and the G value, which is basically more than 0.9 as well. So more or less we are a clear float glass is there.
Right.
And the so these two properties can also be described in terms of relationship, which is basically gives the selectivity or luminous efficacy of a glazing, which is the ratio between TAUVIS divided by G value.
Okay. Very nice.
That tells us how good the technology is in transmitting visible radiation, so light, compared to the transmission total solar radiation. Okay, so ideally, what we would like to have is maintaining the visible transmission as high as possible, not to affect or to reduce the energy used for lighting and to have enough daylight, but to be able to control the G value, so to be able to reduce the total solar energy transmission as much as possible. So what we would like to do ideally is from a clear float clear glass, so in order to control G value and to have a high enough visible transmission, we would like to move towards basically this line of maximum selectivity that we could achieve.
That's our, let's say, target.
Yeah.
And okay.
And this target, going towards this target, is made possible by use of cavity in double glazing units. So this is a section of double glazing units. That's out, that's in. So by using coating in the seals, in the sealed environments, we could basically cut different part of the transmission, the solar spectrum, so to maintain the visible transmission as high as possible, without and reducing the G value as much as possible. So normally the kind of coatings technology nowadays that is the standard, it's coating technology is based on a thin metal oxide layer. So for example, silver oxide, it has the capability of reducing the transmission in the near infrared part of the of the spectrum.
And where would you put it? In the cavity?
It depends on the application. So Lowy coating, so-called single silver oxide layer, so just one layer of among the other layers of silver oxide, is normally placed on phase 3 of a double glazing unit, so internally.
Just to cut the thermal radiation transmission.
The far infrared, which in a way reduces a little bit the transmission, cuts a little bit the G value in a double glazing unit, but not so much. So you are improving the selectivity of the clear glass a little bit, okay,
right,
by using a Lowy coating that is mainly used to reduce U values or reduce heating, not much solar control. So
not for this.
in order to have solar control, you use a coating eventually here on the outside part of the cavity.
Makes sense, because we want to prevent the unwanted solar radiation to go inside.
Exactly. So by using more than one metal oxide layer, silver oxide layer, you are able to cut more and more the infrared parts of the transmission of the solar spectrum. So you would reduce a little bit visible transmission, but not to and you're reducing so much the G value by using more than one silver oxide layer. So this is going to be for double silver.
Okay.
And then you have triple silver, so reducing even further the visible transmission a little bit, but cutting the G value even further, very close to the physical limits.
So they are much more selective.
So exactly, here we are in the order of 1.7 to 2, here we are almost 2.2, 2.3 selectivity. Okay, so we have maintained the visible transmission as high as possible, but we have reduced the G value so much. So this is the standard technologies that are available today. In the past, it was done in different ways, and you can see, let's say, all the different technologies and the points. Each of these points represents a different coating in a double or triple glazing unit. You can see it here.
This is the same graph.
In the same graph with all the technologies together, and a little bit of history of how it was done previously by tinting the glass, for example.
Right. I can see now, I understand very well the graph.
Okay.
But then, for instance, typical regulation limit of a G value.
Yeah. So a typical regulation limit, so a R-stop, it's, for example, in Italy, but to see another nation, is 0.35.
More or less around that number.
Yeah.
Okay, so there are potentially glazing technologies there.
Yeah, and there is not a regulation limit on the visible transmission. That depends on the amount of daylight going in, amount of window to wall ratio. But there are other R-stop on the solar energy that depends either on the overall energy performance or on other factors. For example, in Italy, we have the solar equivalent area that reduces the limit of G value in summer even further, which means that eventually, if you want to do this kind of solar control just with the glass, there are not many technologies available out there. You can use selective coating technologies, but at the cost of reducing the visible transmission.
That would be super low.
The visible transmission a lot. So eventually you need to find strategies in summer to reduce the G value to a very low number, but in winter or when you have a lot of heating demand, instead to being able to have a higher G value and not to reduce so much the visible transmission.
So this is really the challenge for achieving buildings that can decarbonize our built environment, but also maintain comfort and well-being.
On the glazing, on the transparent part of the building envelope, yes. Here in Torino, for example, you can go and have a look around. There are a lot of new buildings. There is a skyscraper next to here, where you can see, for example, example of technologies that are basically double, triple glazing with double silver, triple silver coatings that are very selective, so-called high performance coating, because they have both solar control and low E capabilities.
Which means that I need one coating.
You just need solar control
both.
that it does both features. So it's low E and at the same time solar control, so reduces the G value a lot.
So this is not, to be in this area, we really need new technologies, I guess.
Yes, you need to have technologies that are able to be selective, so reduce the G value as much as possible. That can be done in different ways, but that in a way can change the behavior between summer or a lot of sun, so low G value, low visible transmission, to moments in which you have a higher visible transmission when there is less sun and higher G value when you are in a warmer period. So you want to switch between this part and this part of the option. Of course, this cannot be done with just the glazing, with the static glazing. So we need to use within the glazing other technologies that could eventually achieve this transition between a higher visible transmission and a little bit higher G value to low visible transmission, low G value.
So it could be a dynamic shading, a blind?
That can be done in different ways. Can be done with a blind placed externally, internally in the cavity. That this will affect the relationship between visible transmission and G value differently.
Or it could be done...
Or can be done, for example, with technologies like electrochromic liquid crystal dynamic glazing that in a way could achieve a dynamic G value visible transmission. But it can also be done by using, for example, ventilation in cavities like double skin, so that they are able to cut solar loads by basically use the ventilation in the cavity of the double skin to reduce the G value, and at the same time integrating blind in the cavity. And we can see some of these technologies
in the lab?
In the lab, but also on the roof upstairs.
Can you show me?
Yes, sure.
Let's go then.
So we are in the roof of our department of Politecnico di Torino, and I brought you here because on one part what we can see is basically the high rise over there. That is a nice example to use of selective coating on an office building where there is a need to reduce a lot the solar radiation, so that the G value eventually, but not only. It's an example also of a double skin facade, so a way to reduce even further the G value by means of ventilating a cavity between double glazing inside and an outer skin, that in that case it's glass louver on the outside. But I brought you here also because we have our testing facility, which is to test the performance of innovative glazing components. So glazing components that in a way can reduce the G value even further in a dynamic way by maintaining the visible transmission as high as possible.
So what we see here are technologies that are still under development, and you are doing research to improve them, to improve the current market.
Exactly. We work a lot in supporting the product developments and to do research on this kind of technologies. So what you see here, Alessandra, it's a triple glazing unit with the outer cavity, which is a bit larger, 30 millimeters. And we use basically ventilation drawn up from these lower vents, mechanical ventilation driven by fan, that is basically removing the solar loads that is absorbed on the glass, and then eventually this so it's heating the air in the cavity, and then this air can be used in different way. So if you just want to reduce the G value, you can expel it outside. So you are not using that air, you have removed the solar part of the solar load. Or in winter, this preheated air can be used then to be sent to the indoor environment to reduce the heating loads as well. So this is one, like a specific example of a technology that uses ventilation in the cavity, on one side to reduce G-value in the summer, but on the other side to preheat air that then can be used inside the building in winter.
And now you're testing the performance of the new system with real weather conditions.
Exactly. So this test facility is mainly used to understand what's the real performance of the system in real condition, in this case south-oriented.
Super. Thanks so much.
You're welcome.